Good morning students. This is the part 7 of our chapter Work and Energy. In this part we will derive some important relations and also study about the potential energy. But before going in detail with this part, let me recall you a relationship that we have established between the kinetic energy and momentum of an object. And that relationship is what? Ek, that is kinetic energy, equals to square of momentum P square divided by 2m. This is the required relationship that we have established in our previous part. Now with the help of this relation, again we derive three important relations. Okay, so let us understand each of these one by one. The first relationship that we can derive with the help of this expression is that first, for a given momentum, the kinetic energy of the object is inversely proportional to its mass. That is what we can write: for a given momentum, the kinetic energy Ek is inversely proportional to mass of the object. Okay students? Now students, you know what is the inverse relation? If kinetic energy is inversely proportional to mass of the object for a given momentum, then we can say if we increase the mass of the object, then kinetic energy will go on decreasing. Or if we decrease the mass of the object, then kinetic energy will increase. Meaning thereby we can say lesser mass will have greater kinetic energy as compared to the greater mass for a given momentum. Suppose we have two objects, m1 and m2. Okay, both have the same momentum p. Let us say m1 equals to 2 kg and m2 equals to 3 kg. Okay students, so it is clear that m2 is greater than m1. Okay, if the second mass is greater than the first mass, then with the help of this relation we can say kinetic energy of the second mass will be less than kinetic energy of the first mass. It means we can say the kinetic energy of 3 kg mass is less as compared to the kinetic energy of mass 2 kg. Why I am saying so? Because we know greater mass have lesser kinetic energy for a given momentum. Okay students, so this is the required relationship that is we have derived. Okay, the second relation we have, suppose there are two objects of different masses but they have the same momentum. Let us say there are two objects of masses m1 and m2. Means the two objects have different mass, but they have the same momentum. same momentum. They have same momentum, say P. Okay, it means there are two objects having the different masses m1 and m2, but their momentum are same. Let us say P. Then what we can derive the relationship between their kinetic energies. So for the first object of mass m1, we can write the kinetic energy Ek1 equals to what? Momentum square means P square divided by mass of the object. So 2 into mass of the object is m1. So we can write it 2m1. Okay. Let us say this is equation number 1. In the same way, we can write similarly. What we can write? The kinetic energy of the second object. Let us say Ek2 with the kinetic energy of the second object. Then it is equals to P square divided by 2m2. Let us say this is equation number 2. Okay, students? Now, if we divide equation 1 and equation 2, dividing equation 1 by equation 2, then what we can get? Ek1 divided by Ek2 equal to P square by 2m1, P square by 2m1 divided by P square by 2m2. So it is equals to P square by 2m1 into 2m2 divided by P square. So here P square and P square cancel out, 2 and 2 cancel out. Then what we have? Ek1 divided by Ek2 equals to m2 by m1. m2 by m1. So this is the required relationship between the kinetic energies of these two objects. What does it mean? If there are two objects of different masses m1 and m2, but they have the same momentum, then only the ratio of their kinetic energy is equal to ratio of the mass of second object divided by mass of the first object. Okay, students? So this is the required relationship between their kinetic energies. Now again we have one more relation. Students, you have to note down these things properly in your notebook. Now here we have supposed that there are two objects of different masses having the same momentum, and we have derived that the ratio of the kinetic energy of first object to the kinetic energy of second object equal to mass of second object divided by mass of first object. This is the relation that we have already derived. Now let us say there are two objects of different masses, but they have the same kinetic energy. Then what we can say about their momentum? What we can say about their momentum? Let two objects of masses m1 and m2, but they have same kinetic energy. Say Ek. Then what we can derive the relationship between their momentum. Okay students. Now here they have the same momentum. So for object of mass m1, for object of mass m1, what we can write? The kinetic energy Ek equals to p square, but here we can write p1 square, that is momentum of the first object, divided by 2 into mass of the first object m1. Let us say this is equation number 1. Okay students. Now in the same way, for object of mass m2, for object of mass m2, we can write the kinetic energy Ek, because both have the same kinetic energy. So again we can write Ek equals to p2 square, where p2 is the momentum of second object, divided by 2 into mass of second object m2. Let us say this is equation number 2. Now again here you can see that both the equation 1 and equation 2 is equal to Ek. Okay, so we can equate these two equations. So let us equate. Then what we can write? p1 square divided by 2m1 equals to p2 square divided by 2m2. Okay, again we can rearrange it as p1 square divided by p2 square equals to 2m1 divided by 2m2. Now from here, if we take the square root, then what we can write? Here 2 and 2 cancel out. p1 divided by p2 equals to square root of m1 by m2. Now here what we get? p1 by p2 equals to m1 is under root of m1 by m2. So this is the required relation between their momentum. Means ratio of momentum of first object to the second object is equal to square root of ratio of the mass of first object to the mass of second object. So this is the required relation between their momentum when they have the same kinetic energy. So students, we have derived three important relationships with the help of equation Ek equals to p square by 2m. Let us summarize the relations. Then what we can write? First, the kinetic energy Ek is inversely proportional to mass for given momentum. Second relation we have Ek1 divided by Ek2 equals to m2 by m1 for same momentum. Okay, and the third relation we have p1 by p2 equals to square root of m1 by m2 for same kinetic energy. So these are the three important relationships on which numericals are framed. Okay, now we will come to work energy theorem. What is work energy theorem? Okay students, now students, what is work energy theorem? Work energy theorem states that work done by net force applied on an object is equal to change in kinetic energy of that object. Okay, what does it mean? Suppose there is an object and if we apply force on that object, then what happens? Its velocity is going to change. If velocity is going to change, then kinetic energy will also change, because you know kinetic energy equals to half mv square. So if velocity is changing, then kinetic energy is also going to change. So the work done by that force is equal to change in kinetic energy of that object. Suppose students, there is an object of certain mass m. There is an object of certain mass m which is initially moving with a velocity u. Okay. Now what happens if we apply certain force on this object of magnitude capital F? Then acceleration will produce in the object. Let us say the acceleration produced in the object be a. Due to this acceleration, the velocity of the object is changed to say v. Okay, and in this journey it is displaced by a distance s. Okay, friends. So u is the initial velocity of that object. When a force F is applied in the object, then object gets displaced by a distance s and attains a final velocity v. Okay, students. Now you know the relationship between the initial velocity and final velocity. We have v square minus u square equal to 2a into the displacement s. If we multiply this equation on both sides by half m, multiplying both sides by half m, then what we have? Half m into v square minus u square divided by half m into 2as. Now here 2 and 2 cancel out, or what we can write? If we multiply this half m within the bracket, then what we have? Half mv square minus half m u square equal to m into a into s. Okay, students. Now what is half mv square? V is the final velocity of the object, m is the mass of the object, and you know kinetic energy is given by half mv square. So if here v is the final velocity and m is the mass of the object, then we can say half mv square is the final kinetic energy of the object. So it can be written as E, K and F for final minus half m u square. You know u is the initial velocity of the object and m is the mass of the object. So half m u square can be written as E K I, means initial kinetic energy of the object. Okay, friends. Now let us see the right hand side. Here we have a term m into a, mass into acceleration produced in the object by the net force which is applied. So according to second law of motion, you know that net force is equals to mass into acceleration produced in the object. So here m into a can be written as F into s. Why? Since F equals to m into a by the Newton's second law of motion. Okay, students. Now and displacement are in the same direction, if the force and displacement are in the same direction, then we can write F into S equal to work done. Here you can see in this figure, the force, the direction of the force, this is the direction of the force, and the object get displaced from here to here. So this is the direction of displacement. Both have the same direction. So F into S can be written as work done. Okay students? So here we can write EK F, that is final kinetic energy, minus EK I initial kinetic energy equals to work done. Or you can also rearrange it as work done equals to EK F minus EK I. Now what is EK F minus EK I? Final kinetic energy minus initial kinetic energy, means change in kinetic energy. So here with the help of this expression, what we have, work done equals to net work done equals to change in kinetic energy of that object. This is the work energy theorem. Okay students? So this is the proof of work energy theorem. Now we will study the potential energy and various types of potential energy. Now students, we will try to understand what is potential energy. So the definition of potential energy is that energy possessed by an object by virtue of its position, or you can say by change in its position or change in configuration. But before understanding the potential energy, it is important for us to understand how the energy is being stored in an object. Let us consider two situations here. The first situation here we have, suppose this is the duster, okay, which is placed here. So at this time, the force of gravity on this duster is acting in downward direction. If we have to displace the duster from this position to here, then we must have to work against the force of gravity which is acting downward. Okay students? So in order to displace this duster from here to here, the minimum force that we require to apply in upward direction is equal to weight of this duster. Okay students? So I have applied a force equal to its weight in upward direction and going to displace it from here to here. Okay students? So I have applied the force in upward direction and there is a displacement in upward direction. It means I have done some work on this duster. So the amount of work that we have done in order to displace it from here to here, that amount of work done is stored in the form of energy in this duster. Okay students? So I hope you get an idea about how the energy is stored in an object. Suppose there is a spring, then I want to compress the spring. So the work that I have done in order to compress that spring, that work is being stored in the form of energy in compressed spring. If I am going to stretch a rubber band, then the force with which we are stretching the rubber band, then it means some work is being done on the rubber band and that work is stored in the form of energy in the stretched rubber band. So the amount of work that we are going to do in order to stretch or in order to compress, or if we are changing the position of an object, that work is being stored in the form of energy. Okay students? So I hope this concept is clear to you, how an energy is being stored. On that basis, potential energy is being classified as two types: gravitational potential energy and elastic potential energy. But again, in order to understand these two types of potential energy clearly, it is important for us to understand what is elasticity. What is elasticity? So students, elasticity is nothing but it is the property or tendency of an object to regain its original shape and size. The property of an object, the property of an object to regain its original shape and size is known as elasticity. There are various materials that you have observed in your daily life, like a rubber band, a spring, or a bow. Okay? Then what happens when you stretch a rubber band, then it tries to come into its original position after being released. When you compress or stretch a spring, then it also tries to regain its original shape and size after being released. So that property through which it tries to maintain its original shape and size is known as elasticity. Suppose students, this is the rubber band. This is the rubber band. This is the original shape and size of the rubber band. Now you stretch it by applying force on both sides. Then what happens? It is being stretched and its shape and size is going to change. Okay? But as soon as you release after being stretched, then it tries to maintain its original shape and size. Okay, student? So the property through which it tries to maintain its original shape and size after being released is known as elasticity. In the same way, you have observed that when you compress a spring and release, then compressed spring again come back to its original shape and size. When you stretch a spring and release, then it also try to maintain its original shape and size. So why they are trying to maintain their original shape and size? Because of a property known as elasticity. Okay, students? So I hope this property is clear to you. Now we will come to the two types of potential energy as gravitational potential energy and elastic potential energy. Now let us consider these three examples in order to understand the elastic potential energy. Here in the first example, you can see that we have a spring and a ball. This is the first situation in which this is the original shape and size of the spring and a ball is kept on the spring at rest. In this situation, we observe that the spring has no capability to do some work on the ball. So the ball will remain at rest in this situation. But what happens if we compress the spring? So here in this situation, you can see that we have compressed the spring. Due to compression, you can observe the shape and size of the spring gets changed. Now as soon as we release the compressed spring, the spring tries to maintain its original shape and size by the property of elasticity. Okay? And when it tries to maintain its original shape and size, it pushes back the ball. That's why the ball throw away. Okay? So we can say compressed spring has some energy. Why? Because when we release the compressed spring, then it applies certain force on the ball, due to which the ball flies off. Okay, friends? So the original spring has no energy. but the compressed spring got some energy. So here in this example we can write compressed spring has energy. Okay. Now let us see the second situation. Here in this example you can see that there is a spring and a block is attached with this spring. Okay. Now in this example you can see that this is the uncompressed spring, or you can say this is the original shape and size of the spring. Now in this situation, this spring has no energy. Why? Because it cannot apply certain force on the block so that the block get displaced. But what happens if we compress this spring? So here in this situation you can see that we have compressed the spring. Due to compression, it got some energy and it pushes the block in forward direction. Okay. Why it pushes the block? Because it tries to maintain its original shape and size, due to which the block is pushed forward. So we can say again, compressed spring has energy, while the original spring has no energy. Okay. Now let us consider the third example. Now let us see the third example. In this example you can see that this is the original shape and size of the bow. Now I am going to stretch this bow, then as compared to this situation you can see that the shape of this bow is being changed. When the bow is stretched, then some energy is stored in the bow, and when I release the bow, then what happens? The energy which is being stored in stretching is imparted to the arrow, and arrow starts moving forward with a certain velocity. Okay. So in this situation again we observe that the original bow has no energy, but the stretched bow acquired some energy which is imparted to arrow, and the arrow gets started moving in forward direction after being released. Okay students. Now if we summarize these three examples, then we can observe that in all these examples the energy is produced or energy is possessed by the object because of change in configuration. Here in the first example you can see that the original spring has no energy, but when the configuration, that is shape and size of the spring, is changed, then it got some energy. In this example again, initially the spring has no energy so that it can push the block, but when its configuration, that is shape and size, is changed, it got some energy and it pushes the block. In third example again, original bow has no energy so that it can throw out the arrow, but when the shape of the bow is changed by stretching, then it got some energy, and that energy is imparted to arrow so that arrow starts moving in forward direction. So in all these three situations, energy is possessed by the object because of change in their configuration, and the energy possessed by the object due to change in configuration or shape and size is known as elastic potential energy. So all these three objects have elastic potential energy. Why? Because the energy is produced because of change in configuration or shape and size. So we can define the elastic potential energy as energy possessed by an object by virtue of change in configuration or shape and size. Okay, so this is the definition of elastic potential energy. Okay students, one more thing that is important for us to understand how the energy is being stored. Means from where does this energy, means elastic potential energy, is coming? Here you know that when I compress the spring, then I am doing some work against the elasticity of the object. When I am compressing the spring, then I am doing some work against the elasticity of this spring, and that work done is stored in the form of energy, due to which the block is being start moving in forward direction when it is released. Okay, here also in this example you can see that when I am stretching the bow, then I am doing some work against the elasticity of the bow, and that work is being stored in the bow, which in turn transferred to the arrow when it is being released. So in all these three examples, work is being done against the elasticity of the object. That's why it is also known as elastic potential energy, because the energy is produced as we have done work against the elasticity of the object. Okay students, so I hope elastic potential energy is clear to you. Now we will come to gravitational potential energy. Let us consider this example in order to understand gravitational potential energy. So students, here in this example you can see that there is a wooden block on which a nail is placed. Now what we are going to do, we have placed a stone just over the nail. So in this situation you observe that the stone has no capacity so that it can displace the nail into the wood. Okay, so here in this situation we can say that stone has no energy. Why? Because it cannot displace the nail into the wooden block. Now what happens if we raise this stone by a certain height from the ground? Let us say we have raised the stone to a certain height h. Then what happens? When we raise the stone to a certain height h and again release it, then we observe that in this situation stone has acquired some energy. Why? Because in this situation the stone can apply certain force on the nail. That's why the nail gets displaced through a certain distance as into the wood. So in this situation we can say stone has acquired some energy. Stone has acquired some energy. Now students, let us consider the third situation. In this situation you observe that the stone is raised again through a more height. If you compare this situation with second one, then you observe that the height through which it is raised is more as compared to the second situation. And again in this situation when it is released, then we observe that in this situation the stone has more capacity of doing work, because the nail is displaced by a more distance into the wood. So here we can say that stone has more energy as it is raised through greater height. To a greater height. So, with the help of this example, we observe that when an object is raised from the ground level through a certain height, then it acquires some energy. But why it acquires some energy? Let us understand. Here we have observed that stone has no energy. Why? Because in this situation the stone is not raised above a certain height. But students, you know that the weight of the stone is acting downward. So if we have to raise the stone through a certain height from the ground level, then we have to do some work against the force of gravity. So in this situation, we have done some work against the force of gravity in order to raise it through a height h. And the amount of work that we have done in order to raise it against gravity, that work done is being stored in the form of energy, with the help of which net is being displaced. Here we have raised through a greater height, so we have done some more work in order to raise through a greater height. That's why some more energy is being stored in the stone, due to which more work is done. So in this example we observe that work is done against the gravity. So the energy being stored in the object is known as gravitational potential energy, because the work is done against gravity. So how can we define the gravitational potential energy? The energy possessed by an object, the energy possessed by an object when it is raised to a certain height from the ground, against gravity. So this is known as gravitational potential energy. I hope the elastic potential energy and gravitational potential energy is clear to you. Why that is known as elastic potential energy and why this is known as gravitational potential energy? Because in this energy we are doing work against gravity. That's why this is known as gravitational potential energy. But in elastic potential energy, we are doing work against the elasticity of the material. So the energy being stored is known as elastic potential energy. So these are the two forms of potential energy: gravitational potential energy and elastic potential energy. Gravitational potential energy is due to being raised through a certain height from the ground against gravity, while the elastic potential energy is due to change in configuration or shape and size.